Science has always progressed through a delicate balance of curiosity, humility, and the willingness to confront the unknown. Yet, modern scientific culture sometimes forgets that its greatest advances were born not from certainties, but from bold questions and the courage to challenge established beliefs. In my recent interview with Peter Doocy on the Sunday briefing on Fox News, I emphasized a point that is often overlooked. The foundation of science rests not on the arrogance of expertise, but on the humility to learn. Expertise, when treated as unquestionable authority, can become a barrier to discovery. It can narrow the imagination and create a rigid framework that filters out ideas simply because they lie outside the boundaries of past experience. This is precisely what happened when comet specialists immediately labeled 3I/Atlas, a newly discovered interstellar object, as a familiar, water-rich comet. They did so based on decades of experience, yet their experience was built entirely on objects originating within the solar system. It is like training an artificial intelligence system exclusively on cats, and then assuming the system can accurately identify a tiger. When the training set is incomplete, the interpretation of something new becomes flawed. Humanity has launched spacecraft, probes, satellites, and even cars into space. These objects now drift through the solar system and beyond, and they should be considered part of the possible population of astronomical bodies. If experts do not expand their conceptual training set to include human-made objects, how can they hope to identify potential technological artifacts arriving from interstellar space? A striking example unfolded on January 2, 2025, when the Minor Planet Center, operating under the International Astronomical Union, identified a new near-Earth asteroid. Initially, this seemed routine, until they realized the object shared the distinctive trajectory of a Tesla Roadster launched by SpaceX in 2018 as a dummy payload aboard the Falcon Heavy rocket. Only a day later, the object was removed from the asteroid catalog, its true nature revealed. Not a rock, but a car. If astronomers could mistake something as artificial and unmistakably human-made as a car for a natural asteroid, imagine how easily a more advanced technological object from interstellar space could be misclassified as an icy rock simply because experts are conditioned to expect icy rocks. The oversight is not malicious. It is simply the natural consequence of a training set that excludes the full range of possibilities. When thinking about the broader cosmic landscape, it becomes clear that Elon Musk, innovative as he is by human standards, is unlikely to be the most accomplished space entrepreneur across the Milky Way's 13.8 billion-year history. There are roughly 100 billion stars in our galaxy, and about 10% of them may host Earth-sized planets in the habitable zone. If you roll the cosmic dice billions of times, the probability that only our planet produced technological beings and spacecraft is infinitesimally small. Many stars are billions of years older than our sun, giving civilizations elsewhere enormous head starts. With just the technology of the 1970s, our Voyager spacecraft will cross the Milky Way's disk within a billion years. A civilization even slightly more advanced, or simply older, could easily send probes across the galaxy, filling interstellar space with technological artifacts. It is not far-fetched to consider that some interstellar objects passing through our solar system might be evidence of such activity. And yet, if comet experts restrict themselves to interpretations rooted solely in natural icy bodies, they will fail to recognize these possibilities. Their expertise becomes a blindfold rather than a lens. This theme of science resisting unfamiliar ideas illustrates a larger issue in the public understanding of scientific progress. People often imagine science as a polished, complete product, as though scientists simply reveal a pre-existing truth in its final perfect form. But real science is a process more akin to detective work than lecturing. It unfolds through trial and error, false starts, unexpected clues, and reinterpretations. When quantum mechanics emerged, it was so counterintuitive that even Einstein struggled to accept it, famously rejecting the idea of spooky action at a distance. Yet this once unthinkable concept is now experimentally confirmed and foundational to modern physics. The discovery of quantum mechanics stands as a testament to nature's ability to surprise us, to challenge our intellectual comfort zones, and to force us to revise what we believe is possible. Despite these historical lessons, many modern scientists resist acknowledging uncertainty. The current academic environment rewards safety, publishing only polished results, avoiding bold claims, and presenting conclusions only once they are beyond reproach. This risk-averse attitude creates a disconnect between science and the public. Press conferences often feature scientists speaking with an air of finality, as though they are teachers and the public is a passive classroom. This reinforces the false idea that science is the domain of an elite group who dispense answers from above. But the truth is far more dynamic, messy, and human. Mainstream science has repeatedly been wrong. Einstein was wrong about black holes and gravitational waves. The once dominant theory of supersymmetry has failed to appear in experiments at CERN, despite decades of hype. String theory, after more than 40 years of theoretical dominance, still has not produced testable predictions. These examples demonstrate that expertise alone does not guarantee accuracy. When I communicate about anomalies like 3I/Atlas, my goal is not to claim certainty, but to highlight the process of scientific exploration. An anomaly, by definition, invites multiple interpretations. Only data, not authority, can determine which interpretation is correct. I welcome the process of proposing hypotheses, testing them, refining them, and allowing the evidence to decide. This openness resonates with the public, which is why I receive hundreds of messages daily from people inspired by genuine scientific curiosity. Many parents tell me their children want to become scientists because they see science as an adventurous journey, not a rigid set of final answers. When people witness scientists thinking out loud, they understand that science is accessible to anyone willing to question and learn. Another issue is the way scientific priorities are determined. The 2020 U.S. Decadal Survey of Astronomy and Astrophysics placed its highest priority on searching for microbial life. This focus led to more than $10 billion being funneled into the Habitable Worlds Observatory, a valuable mission, but one that sidelines the search for technological signatures. Microbes may indeed be more common throughout the universe, but advanced civilizations could be easier to detect. Their technology may leave clear indicators such as industrial pollutants, engineered structures, radio signals, interstellar probes, or energy signatures. It makes little sense to invest billions exclusively into one line of investigation when the universe may be offering us multiple pathways to discover life. The public whose taxes fund these missions is far more excited about the possibility of extraterrestrial civilizations than the prospect of discovering microbes. While scientific priorities should not be set by popularity alone, public interest should not be dismissed. The public funds research precisely because they believe in its capacity to answer profound questions, such as whether we are alone. Interstellar objects provide a rare and extraordinary opportunity to study both primitive and technological life. Unlike distant planets that we can access only through telescopes, interstellar objects pass through our own cosmic neighborhood. They can be intercepted, studied up close, and even sampled directly. Missions like OSIRIS-RX have already demonstrated our ability to collect samples from asteroids and bring them back to Earth. If we were to land on an interstellar rock and analyze it, we might uncover organic molecules or chemical signatures that reveal the building blocks of life from another star system. But the potential is even greater if the object is not a rock, but a technological artifact. Imagine landing on an interstellar probe with markings, panels, or even buttons. The philosophical, scientific, and existential implications would be unprecedented. Each detail, its materials, construction, power source, or embedded information, could redefine our understanding of life, intelligence, and our place in the cosmos. The question would naturally arise: should we press the buttons we find or leave them untouched? The answer would require ethical reflection, caution, and scientific foresight. Ultimately, the reason I speak publicly about these ideas is to remind people that science is a living, evolving process. It thrives when we ask bold questions and consider possibilities that seem unlikely, uncomfortable, or unconventional. If we restrict our thinking to what is already known, we will miss what is waiting to be discovered. The universe is vast, ancient, and filled with mysteries. Humility, not arrogance, is what allows us to explore it with open eyes.